about simulation and how to predict the degradation of battery and cells. The second webinar was about the simulation and how to predict the thermal management and thermal runaway and how to avoid it. Today, our topic today is analyzing how a minimal amount of data can be used to obtain degradation and design parameter to better predict battery and cell behavior. Today, with me and with us, we have Prashant Srivastava. Prashant is the current Chief Technology Officer, CTO of Urja, bringing over a decade of experience in the computer-aided engineering field. An experienced developer, Prashant has strong skills in C++, Linux, structural engineer, structural dynamics, and Java. He holds a PhD in aerospace aeronautical engineer from the Indian Institute of Science. Good morning, Prashant. Can you hear me?
Yes. Hi, Marcelo. Good morning, and good morning, everyone.
Good morning, Prashant. First of all, thanks for your time. Prashant is going to share with us his experience in batteries. But Prashant, before moving on, let me say some information to our participants about this webinar.
Sure.
For questions, you should see the question and answer toolbox in the Zoom window, where you can write your questions. Prashant and I will answer all your questions after the Prashant presentation. Tomorrow, you will receive an email with the link to watch this webinar again, if you want, of course. The link with the presentation and the link with the video of the past webinar. So, Prashant, if you agree, we can start with your presentation.
All right. Thanks a lot, Marcelo, for the introduction. And let me share my screen. Can you see my screen, Marcelo?
Yeah.
Thank you, and good morning, everyone. Today, we are going to talk about accelerated live testing with Urja. And we will, so agenda for today is that I'll cover how using Urja you can reduce the testing time for the cells for the warranty estimation. And towards the end of the presentation, I will also run a live demo where I can take you through the steps needed for doing such analysis. But before that, I'll be covering the overall workflow and the kind of steps one needs to take to accelerate this live testing compared to when you do the experiments for determining the life of the cells and hence the batteries. So we at Urja strive for simplifying the complex engineering designs from design to deployment, and we started by looking at the battery problems first because one of the things we realized is that the batteries are very well suited with the methodology we have come up with, which is the hybrid methodology, which you see on the right, where we can combine the information from various areas and make use of them to do the accurate predictions, design optimizations, performance optimizations. I mean, the way it works is that you have experimental data or the data coming from BMS, and you combine the information from the physics, and as well as on top of it, we have machine learning models. And when combine all these things together, we ensure that you get reliable and accurate estimates on the different aspects of the batteries. Now, the advantage of combining, having these hybrid methods is that the physics comes with the physical insights of what is happening in the batteries, whereas physics always has certain assumptions on the models that we are trying to implement in the physical systems, and which in experimental or field conditions might not be accurate. And that is where the machine learning can aid the accuracy by looking at the field data or the experimental data, so it can bridge the gap between the physics-based predictions to what you observe in the field. Now, we have solutions for every stage of the life cycle for the battery. So starting from cell qualifications, design optimization, to degradation analysis, and as well as the real-time monitoring where we can deploy the solutions on board. But today, what I'm going to focus on is this aspect where we perform the degradation analysis as well as the warranty estimations of the batteries. What's the challenge with the warranty estimation? First of all, is that often the battery life goes somewhere close to 8 to 10 years. Now, if you were to really know that what is going to happen in the battery for in these 8 to 10 years, you need to run these long experiments. And particularly for this period of time, the operating conditions also change. So it is not that you can just keep the tests in one particular environment and based on that you can talk about the life of the batteries, because they undergo different operating conditions as well as environmental conditions. Usually what is done is that you do the stress testing of the batteries where you look at the parameters or the operating and environmental conditions in the extreme, try to see that how quickly it degrades, and based on that you extrapolate these results for the actual use cases. Now, often these kind of behaviors are very nonlinear, and it is not that easy to extrapolate the accelerated test information to the real life predictions. That's one of the challenge. Other side, if start by doing the physics modelings, the first challenge you encounter is that you need a lot of parameters which go into the physics to accurately model these batteries. And some of these parameters are the parameters which are used during the manufacturing. For example, it could be the transport parameters in the electrodes, electrolytes, as well as the material parameters of the constituents. And at the same time, you need to also look at the degradation models and get a hold of degradation parameters. Getting all of these things for a person who is not manufacturing the cell is very difficult.
Sorry, Prashant. Can you please hide the little screen, the little window? Yeah, that one. Thank you very much.
Thanks. Yeah. So what I was saying was that if you were to rely on the physics-based models alone, what's going to happen is that you will need so many parameters to do your simulations. And to capture the knee behavior as well, I mean, you need advanced models which can kind of dictate the knee behavior as well as estimating these parameters accurately. So both of them in the standalone way have their own challenges. We at Urja, what we do is we combine both of these together to get the insights from the test data as well as insights from the physics-based models and try to get an accurate estimates on the life of the batteries. Another challenge that you encounter when you look at only the early beginning of life data is that in the beginning, if you look at the cell degradation curves or the resistance curves, they might look very similar. But I mean, towards the later part of the life, you will see that they start deviating. So, it is also sometimes very difficult to just extrapolate things just this way to say that, this is what is going to be the future behavior. So you need much more complex models to capture these, as well as, a bit of, insights from the field data itself that, can distinguish that, what was so different in the different cases that, the degradation behavior was different. Now, hybrid models enable this. They can give you the increased accuracy because they are also being trained on the real life data. You have physical consistency because at the back of it we are also making sure that it is physical. The governing differential equations are being satisfied over there. And then, like I said, that when you look at only the beginning of life data or few cycles of data, and you want to extrapolate, that extrapolation becomes much more complex in this case. But both combination of physics and the database learning can improve these extrapolations. At the same time, we have come up with the methods which can do these computations faster and can basically help you predicting multiple scenarios quickly and thus estimating your warranties much earlier than what you would typically take when you were to just rely on the experiments. So when you look at the typical accelerated testing, you need to do the extensive cycler testings in different conditions, and then sometimes you do only it for limited period, and the accelerated conditions again are the extreme conditions. So you need to do some amount of analysis to say that what it will translate to when it comes to the real life uses. All that requires some time. So typically 15 months of time for even the cycler testing, even if it is accelerated testing, and then you will do certain analysis from this data, which would take anywhere between 1 to 2 months. And we at Urja can design certain intelligent experiments to determine the physical behavior, which would take only 2 months of testing, and then simulating all these responses on the different conditions can take you another 2 months, and thus reducing the overall. And with this, you can analyze the data and come up with the warranty estimates, which would reduce the testing time significantly. Now, the approach that we use at Urja for doing this is that we first start by doing the beginning of life characterization. So for which we start by conducting the HPPC tests on the cells at room temperatures and if possible at different temperatures as well, just to capture the temperature dependence on the parameters. So with the HPPC test, we try to determine the beginning of life parameters for the cells, which is the transport and design transport parameters in the cells, which could be something related to, for example, the diffusivities in the electrodes, diffusivity in the electrolytes, and reaction rates at the electrode surfaces and things like that. All of that information can be determined by training our models on HPPC tests. And once we have the beginning of life model, next thing we need to do is to map the degradation behavior of the cells, for which we again need accelerated cycle test data up to 300 cycles. And with this, we also try to map the degradation behavior based on the different mechanisms that are already present in Urja. These mechanisms include, for example, the SEI layer growth, then lithium plating, and loss of active materials, as well as additional SEI layer growth once the particles start cracking due to the stresses. So all of that parameter can be estimated using this accelerated cycle life data. And once we have these parameters estimated, you have a model for the cell. And now you can run it in different scenarios and look at the battery behavior, that how it is going to degrade, how it is going to perform over a period of time. So essentially, you can run it over duty cycles, which is the dynamic environment or the way you will use these batteries in the field. You can analyze with slow and fast charging and what impact it has on the degradations, and then even analyze the storage conditions, which is typically useful for the calendar life. So let's say that if the battery is kept idle for a time, over the period of its uses, how it is going to affect your calendar life. So both cycle life and calendar life can be combined together to estimate the warranties. And then there are different patterns that you can analyze the behavior for. For example, sometimes you control the depth of discharge just to extend the cycle of the life of the batteries, because at high extreme conditions, at the high state of charge or low state of charge, that the degradations are significant, and in those cases you can experiment with the optimal depth of discharge to get the optimal life, and similarly the operating and ambient conditions. So all of these what if scenarios can be performed, and with the simulations, and these simulations are way faster, so you should be able to simulate many cases within, like I mentioned earlier, within 2 to 3 months. Now, Just elaborating further on this process, so like I mentioned that we first start by identifying the cell material properties at the beginning of life, which I was mentioning that we use SPPC data. So here you typically see one example where we have conducted a HPPC test experiment. And then what we are doing is we are trying to identify the parameters in the cell which can exactly give us the same behavior as seen in the HPPC tests. And this helps us in identifying all these transport parameters. And that also kind of guarantees that the model that we are starting with for the cell is capturing really the real life cell behavior. Then what we do is we look at the degradation data. So with the accelerated test data, we want up to 300 cycles of training data. Based on this, we further estimate the degradation parameters for the different mechanisms that, like I mentioned before. And once we have these degradation parameters, what we do is for the same set of training data, if the test was conducted for the end of life, what we do is we try to continue our predictions on the same set of data just to ensure that we are able to capture that behavior. And once we are satisfied that the behavior is captured accurately for the degradations in future, then you can use this model in different scenarios. Now you can use it for different seed rate combinations, different temperatures. And here in this case, we also try testing that once we have trained it at 0.3 C and 0.5 C rates, and what happens if we do the predictions on 0.3 C, 1 C case. In this case, you can see that it is very much matching with the observed data. And similarly, you can study the different combinations, temperatures, C rates, and things like that, just ensuring that the model is accurate enough. But here, as you can see, that there are certain gaps in the predictions, which would happen because the physical models again have certain assumptions. So if you just rely on the pure physics models, then we know that because of these the things which are missing in the model, it can still deviate. And so before I get into the hybrid methodology, I just wanted to also highlight the impact of ambient temperature. So, the temperatures across the world changes significantly, and also with the seasons. And you would find that the batteries degrade differently in different ambient temperature conditions. Now, here is one example where you can see that when you go to close to 0 degrees Celsius, the battery life is very, very low because of the lithium plating being the dominant over here, and that can impact the overall life of the cells. So if one has to improve the life of the cells, either they can have the preheaters built in just to ensure that it is operated at optimal temperature, and also it helps you identifying the risks in your warranty estimations if you know that it is going to be operated in varying environmental conditions. Right. For our verification purposes, we also tried running the trained models on the experiment and compared it with the experimental, with the field data which was observed experimentally. In this case, you can see that once we have trained our models, we tried to see if we can capture the cell behavior from the experiments. And here, both SOC and cell voltages we were able to capture accurately based on our estimates on the parameters for the beginning of life data as well as degradation data. Now, coming to the warranty estimation, so how does it all help you in doing the warranty estimation? So one of the thing is that you start by analyzing the different scenarios and look at what would be the life in different conditions. Other thing that we do is we now start combining it with the hybrid models. So earlier, what you saw was purely physics-based models, which were combined with experimental data to tune these models. But then once you have the accurate physics models, you can combine the experimental data as well as physics-based results to train the machine learning models and make them generic enough, and also it helps you doing the faster predictions, because once the training is done, prediction times are very quick based on the data. So here what we highlight is that we tried training our machine learning models on SNL data, and in this data you would see that the cycler was reset multiple times, and because of which there was some amount of recovery of the capacity because of the reset of the cyclers, because the cell had time to relax, and thus leading to a very nonlinear behavior. We could capture all of that nonlinearities in our machine learning based training model. And if you look at the different predictions that we did on the state of health at different cycle conditions, you would see that the predictions were quite accurate, on the I mean, when you compared it with the experimentally observed data. Now, with all these things, what you can do is you can generate the degradation envelope, which essentially means that you can start by designing the experiments, which includes the temperatures, depth of discharge, C rates, etc., and even the drive cycle conditions, different kind of drive profiles, and you can start generating this envelope. And based on this envelope, you would know what is the worst life or the best life for the cells. And once we have the map of this, we look at the most probabilistic estimate on this, where if a lot of conditions are leading to one particular life, you would essentially
Prashant, I think we have some. Prashant, can you hear me?
I can hear you.
Okay, okay, perfect. Sorry.
Okay, can you hear me?
Yeah. Some connection issues before, so don't worry.
Right. Okay. So with this, I will quickly do a demo of the tool, and just to take you through the steps involved in modeling all these things, and then we can take up the questions, right, Marcelo?
Sorry, Prashant.
What I was saying was that then, with this, I can just demo the tools where
Yeah,
I
for
can
sure.
highlight the steps, and then we can take the questions.
For sure. Thank you.
All right. The Urja is a web-based tool. So once you log in with your credentials, you see this kind of a window where you have different apps listed over here. So, I mean, let me go to home screen first. So this is what you will see when you log in, and so here you can create different projects for different analyses. And what I'm going to do is, here there are shared spaces as well. So just to highlight that in Urja you can also share your models with others. So once, let's say, you have performed your analysis and you want to share these models with someone else in your group, or across different companies who have the access to the license of Urja, you can share it with them as well. But right now, what I'm going to do is I'll use one of these models just to take you through the steps. So the way it works is that you first start by creating the cells in Urja. So that is, in the materials you have the cell nodes, and for the basic uses, in the cell you just get to see the basic information, thermophysical properties, as well as the form factors of the cells and the basic chemistry. But suppose if you wanted to do degradation analysis or cell performance analysis, and you have access to the design as well as transport parameters, in the advanced settings, you can specify all of those parameters. And like I was mentioning earlier, that these parameters, the list of these parameters is huge. And that's what poses one of the difficulties, that if you were to model it physically, you will need access to all of these parameters, which is what makes it tougher. Now, to help users, what we do is we try to get these parameters or identify these or some of these parameters at least by doing the optimization, for which we first need the data. So in this case, like I mentioned, that we want HPPC data. And once you have uploaded the HPPC data, we can do the basic processing, and where we can identify what were the C rates of the pulses and things like that. And once this data is processed, you can use it in the HPPC optimization application. So this is where you just link your data, and then you specify the threshold current. And then here is the advanced setting for different kind of optimization constraints. So for example, what is the variance weight, population size, and things like that, which is advanced parameters that you will get to know once you refer to the documentation. But what happens is that once you run optimize, for example, it tells you the initial guesses of the different parameters that we are using, what are the bounds of these parameters. And once you start the optimization, what happens is that it starts with these initial guesses and tries to explore the space within these bounds to see that which combination of these parameters can reproduce the behavior observed in the experimental HPPC data. And so thus, you would get a hold of the transport parameters for the cells with this analysis. And then you can skip all of these apps. Particularly for the degradation analysis, we go to fade. In fade, we have two different categories: physics as well as hybrid. In the physics, you have two-step process where you first train the models. When I say train the models, it is about identifying the degradation parameters, like we discussed in the slides, where you upload a degradation or accelerated test data, and we try to figure out what are the different parameters causing these degradations. So with the training, for example, you upload a data and then you estimate your capacity based on the identified parameters and make sure that it is capturing the patterns. And here is the list of the trained degradation parameters. So once you are done with the training these models, you will get this updated list of the parameters causing the degradations. So here you can see that it is diffusivity of the SEI layers, the lithium plating and stripping rate constants, and loss of active materials. So all of these degradation mechanisms are governed by these parameters. You can refer to the documentation for knowing about more details about these parameters, and the documentation is available by just going to the tab over here, so where you can go to different applications to know more about all these uh, more about the applications. Right. So once we have identified these parameters, then we go to the prediction models, and where what you need to specify is, for example, the end of life criteria, your number of prediction cycles. You have cycling based on voltage limits as well as SOC limits. And of course, the initial SOC when you are starting the cycling, and then different kind of charge and discharge profiles. So for example, you can do a simple constant C rate charge, constant voltage charge, followed by constant C rate discharge. But then we provide different methods of charging and discharging. It could be discharged at constant power, or you can also use your drive cycle, for example, to do the drive cycle analysis. In this case, for example, if you have a current versus time data, you can upload that data over here for performing your simulations. It could be in the form of a power versus time as well. So all of that is supported over here. And other than that, if you have complete duty cycle for the cell and you want to use that duty cycle to run the simulations, you can do so as well. In that case, you will upload that file for the duty cycle. Here for the temperature conditions, you have the constant ambient temperature conditions, in which case you can just fix the temperatures. Otherwise, if you know that the vehicle is running through the seasons and you want a varying temperature to be accounted, you can upload a file of the temperature variations across the period, and then it can account for the temperature variations from the ambient as well. And this is where you can include the calendar aging models. So it is just a click of checkbox, but the model parameters for the calendar aging are also available in the advanced settings for the cell. And here with the advanced settings, you can select and deselect different degradation mechanisms if you want to study the individual degradation effect of the individual degradation mechanisms. And below there are certain settings for tweaking the solvers. All right, so with this prediction, you will get the degradation patterns, SOH, throughput, as well as capacity versus time. You can also look at behavior of different degradation mechanisms, for example, the active material fractions. Because it is done for 1,000 cycles, it is a huge amount of data. It takes some time to load over here in the user interface. But essentially, you can look at the active material fractions, ACI thickness growth, plated lithium, and things like that to analyze the degradation behaviors in detail. Right, and then for the hybrid models, what you do is you make use of the physics-based prediction data as well as the experiments data that you have. So what you can do is you can upload all of the data as a zip file, and it can basically upload all of the different cases, and all you need to specify is the nominal capacity, minimum and maximum operating voltage of the cell, and then based on this, it can read all that information. And if you have, for example, in the experiments, if you have RPT which is performed periodically, then it can make use of that data as well to estimate the capacities and trains this model based on the experimental observations. So here in this case, you can see a very good correlation with the experimental test data to the trained values. And the approach is very similar. You can then go to, again, prediction models, where in this case it is not created here, but what you can do is you can just choose the algorithm which you want to use. In the previous case, we had particle swarm, and then you can link it with the training model. And then here you can upload your input data as well as the base cycle information if you have. For example, in the beginning of life, if you had conducted one cycle test, you need to upload that as a reference, and then it can tell you the degradation behavior using that training model. All right, so that is what I have to talk today. And Marcelo, we can take questions if there are any.
Thank you, Prashant. Yeah, we have 3 questions. First of all, while performing accelerated life testing, RPT needs to be done periodically for accurate state of art estimation. How do we address this?
So the question is that for the degradation testing, do we need to do the RPTs periodically?
Yeah.
Right. So what happens is that when you are doing the dynamic cycling, often because you are operating at higher C rates, it is impossible to completely charge or discharge the cells, and hence you will never know the right estimates for the capacity at that moment. So usually RPTs are done to ensure that we do this slow charging and discharging of the cells, so that we have correct information on the cell capacity. And for when you are doing this accelerated life testing, usually it becomes essential to do the RPTs just to know for example, for the correct capacities. And what happens is that with the hybrid models, what we can do is we can make use of this RPT test data, train the models, and then eventually, if you are doing the subsequent cyclings on the new cells, we can choose not to have the RPT cycles present in the testing, uh, what we can do is based on the trained models, you can replace the RPTs completely and you can predict your state of health based on the trained model itself. And that will save you a lot of time because RPTs are usually the slow tests where you do the charging and discharging at slow rates, you do the HPPCs and things just to know the cell parameters, which can be reduced if we are making use of the hybrid models to doing these predictions.
Thank you, Prashant. The second question is, the range needs to be determined at different state of health levels. Can Urja help to understand the impact of aging on range reduction?
Right. Yes, indeed. For range analysis, we have application. Let me go to the. So there is an application called range over here. This can be used for studying the range reduction as the cells or battery packs degrade. Uh, this application essentially, based on the vehicle specifications, calculates the power required for the vehicle, as well as once you upload the drive cycle. In this case, the drive cycle is in terms of velocity versus time profile. So once you have all that, we internally calculate the power required for driving the vehicles with that kind of a velocity profile. And for that power profile, you can also calculate that how long the car can run or any vehicle can run with that battery. And what happens is that as the battery degrades, there are two things that happen. One is that the capacity gets reduced. So, and the other thing is that the internal resistance of the battery also increases. Now, what you can do is you can basically when you are selecting the cell, for example, so there itself you can specify that that it is a degraded capacity or it is the beginning of life capacity, and you can do the parametric analysis of at different states of health to estimate the range over here. So for range estimation, you need to tick this checkbox range estimation, and then for a given drive profile, it can tell you the range. And all you need to tell is that at different states of health, what was the capacity and the internal resistance of the cell.
Thank you. We have a few other questions. How do you estimate power fade due to aging?
Sorry, Marcelo, can you repeat again?
How do you estimate power fade due to aging?
Power fade, yes. So
Yeah.
we give you the internal resistance uh, increment as well as the cells age, and hence you can also get an estimate on the power fade. So essentially, as the internal resistance of the cell increases, the amount of power that is available from the cell is limited because you have typically a limit from the BMS that it cannot go below a minimum voltage. And as the resistance keeps increasing, the margin for going to the minimum voltage is reducing because of the IR drops in the voltage. And that can be determined by looking at how much internal resistances have increased.
The last question, to predict the key point, do we need any experimental data supporting when a key point occurs, or the model can predict occurrence of the key point using the data from 300 cycling for modeling training?
To predict what, Marcelo?
The knee point.
Knee point, okay. For knee point, yes. So sometimes this 300 cycles of data is not enough for predicting the knee points because a lot of things happen in the cell much later. So what we also try to do is, we mix the physics-based training up to 300 cycles of data together with some tests where we have seen the knee points with the hybrid model. So what we do is we have certain tests performed for the knee points experimentally, and then a test from the physics, which are based on the training the models and generating the data for the different scenarios. And once you mix these two different data sets and train your hybrid model, then you should be able to predict the knee point as well.
Thank you, Prashant. I don't see any other questions, so I want to thank you once again for your time for your presentation. Just let me share my screen.
Thank you, everyone.
So if you want any other information, you can write to me, and you will receive another email tomorrow with the presentation, with the video, and with the other information. So thank you everyone for joining us, and thank you, Prashant, once again for your time and for your presentation, and thank you everybody.